Hey, Calculus 2 fans. Today we're going to be talking about inverse trigonometric functions. Now, as far as inverse functions go, remember this. If f of x and g of x are inverses of one another, then f evaluated at g of x equals x, and g evaluated at f of x equals x. F and g undo each other through function composition. And typically, we'll denote g as being f inverse of x. If g is the inverse of x, typically we'll represent g as f inverse of x. Or if we want to call f of x the inverse of g, we'll denote x as being g inverse of x. And this is how inverses react with one another through function composition. F inverse evaluated at f of x equals x. They undo each other through function composition. And f evaluated at f inverse of x equals x. Again, f and f inverse undo each other through function composition. And we can make the same statement with g and g inverse. G inverse evaluated at g of x equals x. G inverse and g of x undo each other through function composition. And it just leaves us with the inner function x. And similarly, g evaluated at g inverse of x equals x. G and g inverse undo each other through function composition. It turns out that each of the 6 fundamental trigonometric functions, sine, cosine, tangent, cotangent, secant, cosecant, each of the 6 elementary trig functions has an inverse. And that's what we're going to look at next. Let's start off with inverse sine. We define the inverse sine function, denoted sine inverse of x, or arcsine of x. You know, that's interesting. The inverse sine function can be written with 2 different styles of notation, and there is some merit for doing that. We'll talk about it in just a second. We define the inverse sine function, denoted sine inverse of x, or arcsine of x, as the function that undoes sine of x through function composition. So in other words, we'll have sine inverse evaluated at sine x equals x, and similarly sine evaluated at sine inverse of x equals x. In each case, sine and sine inverse undo each other through function composition. Now, let's look at the alternate notation, arcsine. And arcsine is the same thing as sine inverse, just a different style of notation. Arcsine evaluated at sine of x equals x, and sine evaluated at arcsine of x equals x. In each case, arcsine and sine of x undo each other through function composition. And before I get to why we have 2 different styles of notation, I'll just mention quickly that the other inverse trig functions are defined similarly. So there is such a thing as a cosine inverse function or an arc cosine function. There is such a thing as a tangent inverse function or an arctangent function, so forth and so on. Now let me get to why it is that we have 2 different styles of notation. There actually is merit for this. Okay, Here's why we have two different styles of notation. Two different styles of notation when it comes to representing inverse trig functions. If f has an inverse, it's customary to represent the inverse of f of x this way. And we look at this and say f inverse of x. Thus, representing the inverse of sine of x as sine inverse of x is quite appropriate. However, it is also customary to represent the sine of x quantity squared as sine squared x, the sine of x cubed as sine cubed x, the sine of x to the fourth is sine to the fourth x, and so forth. Those of you who had me for Cal 1, you remember me telling you that I hate this style of notation. It goes right up my you-know-what when I see this. I hate it. But it's been in use for centuries. We're not going to get rid of it. I don't like representing sine of x quantity squared this way, but it's been in wide use for a long time, and there's nothing we can do about it. It's like when we go into that movie theater with our girlfriend and there are only 2 seats left. So we sit in those 2 seats right next to some big 9-foot-tall, 800-pound biker guy who's got knives inside his belt here and has a semi-automatic weapon in his lap. He's being real obnoxious, and your girlfriend elbows you in the ribs and says, well, don't just sit there, make them stop. Hey, we may not like it, but there's nothing we can do about it. Same thing here. We may not like this style of notation, but there's nothing we can do about it. It's been in wide use for a long period of time. We're not going to get rid of it. Nevertheless, we have a paradox. And here it is. Therefore, there is some ambiguity as to how we should interpret this. Do we interpret this as being sine of x raised to the negative 1 power, which is 1 over sine of x, which in turn is cosecant of x? Or do we interpret this thing as being the inverse of sine of x? These are two very different things. The inverse of sine of x is not at all the same thing as sine of x to the negative 1 power. So when we see this notation, sine negative 1x, do we interpret it as sine of x to the negative 1 power, as we do with this style of notation? Or do we look at it and say, oh, this is sine inverse of x, the inverse of sine of x? Which is it going to be? Now we can see whichever way it is, there's going to be some confusion. So here's the answer. By convention, universal mathematical convention, this symbol, sine inverse of x, always represents the inverse of sine of x. Whenever we see this, this is always interpreted as the inverse of sine of x, the function that undoes sine of x through function composition. And by universal mathematical convention, this symbol never represents sine of x to the negative 1 power. If we are talking about sine of x to the negative 1 power, we'll label that cosecant x, 1 over sine of x is cosecant x. So this never, ever, ever represents sine of x raised to the negative 1 power. That is the universal convention, so that we don't misinterpret what is meant by this notation. Nevertheless, some people decided that maybe it's just better to avoid this altogether, and instead of writing sine inverse of x, they write arc sine of x. And arc sine of x, arc cosine of x, that style of notation is also in wide use. We will use both styles of notation. I think our text uses both styles of notation. But we'll always remember that when we see this, we're talking about the inverse trig function. We're never talking about that trig function raised to the negative 1 power. Note something. The angles that we plug into the sine function. Let me stop for a second. Let me try this again. The expressions that we plug into the sine function are the measures of angles. What are we going to put in here? A ham sandwich? No. What we plug into the sine function is the measure of an angle. Therefore, if we're given y equals the sine evaluated at x, and we take each side of this equation and plug it into the inverse sine function, we get inverse sine of y equals inverse sine evaluated at sine of x. And since they're inverses, they undo each other. That is, we get sine inverse of y equals x, or x equals sine inverse of y. Now, what does this mean? X equals sine inverse of y. In other words, how do we interpret this equation? Let's see. Just to recap, here's what we started with. We started with y equals sine evaluated at x. And of course, what do we plug into a sine function? The measure of an angle. X is the measure of an angle. So y equals sine evaluated at x turned out to be equivalent to this. X equals sine inverse of y. Now, how do we interpret this statement? Well, since this statement is equivalent to this statement, we interpret it exactly the same way. But we interpret it this way. X is the angle whose sine is y. So whenever we see this, x equals sine inverse of y, we interpret it this way. X is the angle whose sine is y. And the alternative notation, we treat that the same way. X is the angle whose sine is y. This is going to be a fairly important observation. As a matter of fact, we're going to make good use of this observation in this lecture. So whenever we see x equals sine inverse of y, let's remember what this really means is that x is the angle whose sine is y. And given x equals arc sine of y, that means x is the angle whose sine is y. Seems like a pretty trivial observation, but sometimes trivial observation, sometimes form of notation, an interpretation of notation is everything. In similar fashion, x equals cosine inverse of y, or alternatively, x equals arc cosine of y. We interpret this as saying x is the angle whose cosine is y. And similarly here, x equals, now we don't interpret this as anything. If I write it correctly, I guess it has an interpretation. There, that's a little bit better. X equals tan inverse of y, or x equals arctangent of y. We interpret that as x is the angle whose tangent is y. And analogously, we do the same thing with the other inverse trig functions. Looking at an equation this way is going to turn out to be very important in what we're about to do. And it's going to be very important later on in the semester when we do things like trigonometric substitution. We're about to hit a snag. And to illustrate what the problem is, let's consider the angle of pi over 6. The angle that this ray makes with the positive x-axis, pi over 6. Cosine of pi over 6 is square root of 3 over 2. The sine of pi over 6 is 1/2. Now let me ask you something. What happens if I start right here at this point on the terminal side of the angle, and I go a distance of 2 pi around the circle? Don't I essentially have the same angle? Doesn't the angle pi over 6 and the angle pi over 6 plus 2 pi, let's see, what is that? 13 pi over 6? 13 pi over 6. Don't these two angles, pi over 6 and 13 pi over 6, represent the same point on the unit circle? And suppose I didn't stop there. Suppose I went around another 2 pi. So let's see, 13 pi over 6 plus 2 pi. What is that, 25 pi over 6? And so on and so forth. If we go around again, let's see, that'll be 37 pi over 6. And so on and so forth. All of these angles, pi over 6, 13 pi over 6, 25 pi over 6, 37 pi over 6, and so on and so forth, they all refer to the same point on the unit circle. And therefore, sine of pi over 6 is equal to 1/2. The sine of 13 pi over 6 equals 1/2. The sine of 25 pi over 6 equals 1/2. The sine of 37 pi over 6 equals 1/2, and we can keep on going. And we can go in this direction too, subtract 2 pi. and we get sine of negative 11 pi over 6 is equal to 1/2, and so on and so forth. Well, so far, maybe the problem is not evident, but we're about to get bit in the behind, and we don't like that. But sometimes in math this happens, and we have to take preventive measures from to keep that sort of thing from happening again. So let's see what the problem is, and then see what kind of preventive measure we can take to keep that from happening over and over again. Here's where the problem rears its ugly head. Remember that the statement x equals arc sine of y means x is the angle whose sine is y. So x equals arc sine of 1/2 means that x is the angle whose sine is 1/2. Therefore, if x is the angle whose sine is 1/2, then x equals ... negative 11 pi over 6, pi over 6, whoops, 13 pi over 6, 25 pi over 6, 37 pi over 6, and off into the sunset. Now, is that a problem? I think it is. We have arc sine of 1/2, or inverse sine of 1/2, being equal to all of these different values. But if that's the case, then arc sine can't be a function. Remember, when we have a function, we plug one value in and we get one value out. Here we're plugging one value in, we get infinitely many values out. So the way things stand, this is not a function. Big problem. This can't be the inverse function of sine of x if it gives us more than one value for each x value that we plug in. So somehow we have to fix that. Here's how we fix the problem and get ourselves out of a very sticky situation. We realize that sine of x only assumes values between -1 and +1. Sine of x is never less than -1. It's never greater than +1. We also recognize that the sine of x assumes every value between -1 and +1. So we take a look at the graph of y equals sine of x. And we notice that from this point on the graph, where sine of x is -1, to this point on the graph, where sine of x is +1, the sine function assumes every value from -1 to +1. And we say to ourselves, okay, when it comes to the values that the inverse sine function can attain, we're going to restrict those values to negative pi over 2 to pi over 2. And the effect will be that if we plug any x value in, if we plug any value into the sine inverse function, any value that sine can assume into the sine inverse function, we're going to get exactly one value, and it's going to be between x equal negative pi over 2 and x equal positive pi over 2. Now, it seems like maybe a clumsy way to deal with this, but it turns out it's the best that we can do. We're going to restrict the values that the sine inverse function can assume to those values between negative pi over 2 and pi over 2. So let's see how this would change the problem that we tried to tackle a minute ago. From now on, whenever we see this, we're going to interpret it this way. X is the angle in the interval negative pi over 2 to pi over 2, whose sine is y. So this becomes x is the angle in the interval negative pi over 2 to pi over 2, whose sine is 1/2. Okay, well that certainly eliminates this guy, and this guy, and this guy, and this guy. And now all of a sudden we have arc sine of 1/2 equals pi over 6. Arc sine, sine inverse, congratulations. You've just been elevated to the status of function. Yay! Now let's look at a few more of these things. We have to make similar concessions for the other inverse trig functions. X equals arc cosine y, or x equals cosine inverse of y. We interpret it this way. X is the angle in the interval 0 to pi, whose cosine is y. So what about this? X equals cosine inverse of 1/2. This means x is the angle in the interval 0 pi, whose cosine is negative 1/2. Okay. Let's see how well we know our unit circle trig. Here's the top half of the unit circle. Here's the angle pi. Here's pi over 2. We have 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6. And right here, the x-coordinate is negative 1/2. The y-coordinate is square root of 3 over 2. So the x-coordinate, negative 1/2. This is our cosine. At the angle of 2 pi over 3, the cosine of 2 pi over 3 is negative 1/2. X is the angle whose cosine is negative 1/2. X equals cosine inverse of negative 1/2. That angle is 2 pi over 3. Guess what? Now we're really going to need to know our trig values for all the angles on the unit circle. Guess what else? It's not nearly as hard as you think it is. Really, all we have to do is memorize the first quadrant, and then there's a very simple trick for figuring out the rest of the unit circle. If it weren't that simple, I wouldn't be able to do it. Here's the concession that we make for inverse tangent. X is the angle in the open interval, negative pi over 2, pi over 2, whose tangent is y. Why can't we include the endpoints negative pi over 2 and pi over 2 like we did with inverse sine? Well, think about it. If x is equal to pi over 2 and the tangent of x, let's see, what would that be? If x is pi over 2, what would the tangent of x be? Sine of pi over 2 over cosine of pi over 2. And what's cosine of pi over 2? 0? If x is pi over 2, then tangent of pi over 2 is undefined because cosine of pi over 2 is 0. Same thing with x equal negative pi over 2. So if we have x equal tangent inverse of y, we restrict the interval that x comes from to the open interval of negative pi over 2 to pi over 2. So let's do a little example. The coach just sent in a new play from the sidelines. We're doing this one. X is the angle in the open interval negative pi over 2 to pi over 2, whose tangent is negative square root of 3. So let's see. We want an angle whose tangent is negative square root of 3. So essentially, since tangent is sine over cosine, sine x and cosine of x have to be in a ratio of square root of 3 to 1. Furthermore, one of these has to be positive and one has to be negative. In the interval from negative pi over 2 to pi over 2, what's going to be negative, sine or cosine? It's going to be sine that's negative, right? Between negative pi over 2 and pi over 2, cosine is positive, so it has to be sine. And we want sine and cosine to be in a ratio of square root of 3 over 2. Well, how many angles between negative pi over 2 and 0 have a sine or a cosine that involves square root of 3? It's either going to be negative pi over 3 or negative pi over 6. And if we have x equals negative pi over 3, sine of negative pi over 3 is negative square root of 3 over 2. Cosine of negative pi over 3 is positive 1/2. So that implies tangent negative pi over 3 is sine of garbage over cosine of garbage, which equals negative square root of 3 over 2 over 1/2, which equals negative square root of 3. So the angle that we're looking for is negative pi over 3. X is the angle, negative pi over 3, whose tangent is negative square root of 3. Similarly, the statement x equals arc cotangent y, or x equals cotangent inverse of y, we interpret that as x is the angle in the interval from 0 to pi whose cotangent is y. And we, again, exclude 0 and pi because they're division by 0 issues. X equals secant inverse of y, or x equals arc secant of y. X is the angle in the interval from 0 to pi over 2, or pi over 2 to pi, whose secant is y. Now you notice to get these two disjoint intervals, all we did was we took the interval from 0 to pi and we removed the point pi over 2. Well, why on earth would we do such a thing? It turns out that if x is equal to pi over 2, then secant of x is undefined. So again, division by 0 issues here. And lastly, x equals cosecant inverse of y, also known as x equals arc cosecant of y. X is the angle in the interval negative pi over 2 to 0, or 0 to pi over 2, whose cosecant is y. And again, I took a closed interval from negative pi over 2 to positive pi over 2 and plucked out the point 0, because if we let x be 0, the cosecant of 0 is undefined. So again, we remove 0 from consideration because when x is 0, cosecant of x is undefined. Now let's look at one more example. X equals arcsecant of 2. Solve for x. Okay. So we interpret this as saying x is the angle, and the interval from, let's see, I'm thinking this is 0 to pi over 2, pi over 2 to pi, whose secant is 2. Heavens to Betsy, how are we going to do this? Well, if the secant of the angle is 2, secant is 1 over cosine, right? Which means that cosine of x is 1/2. X is the angle in the interval from 0 to pi over 2, or pi over 2 to pi, whose cosine is 1/2. It's in the first quadrant. What angle in the first quadrant has a cosine of 1/2? If you said pi over 3, you are right. Now, how are we going to keep all of these things straight? How do we keep the ranges of the inverse trig function straight, or the set of values that each trig function can assume straight? How do we do that? There's sort of a memorization trick. sine associated inverse trig functions. And essentially the range is going to be negative pi over 2 to pi over 2 with some modifications. Now, what do I mean by sine associated inverse trig functions? Sine tangent, which is sine over cosine, and cosecant, which is 1 over sine. So I'll call all of these sine associated functions. Inverse sine, inverse tangent, inverse cosecant, they're all going to have ranges between negative pi over 2 and pi over 2 with some modification. Either we're going to have to pluck out the midpoint or maybe exclude the endpoints. But essentially we go negative pi over 2 to pi over 2. And then we have cosine associated inverse trig functions. Inverse cosine, cotangent, because that's cosine on top and sine on the bottom, and secant, because that's 1 over cosine. So inverse cosine, inverse cotangent, inverse secant all have a range from 0 to pi, essentially. So we can associate cotangent and secant with cosine because cotangent is cosine on top over sine. Secant is 1 over cosine. So we have cosine, cosine, cosine. The inverse cosine, the inverse cotangent, the inverse secant, they all have the same range. It's the same as the inverse cosine. Then we have our sine associated inverse trig functions. Sine, tangent, and cosecant. We associate these together because tangent is sine up top over cosine. Cosecant is 1 over sine. So we have sine, sine, sine. And we associate inverse sine, inverse tangent, inverse cosecant with one another as far as having the same range. Negative pi over 2 to pi over 2. Now think about it for a minute or two. Before we proceed further with inverse trig functions, we're going to have to define algebraic and transcendental functions. An algebraic function in the variable x is a function that can be created by performing a finite number of additions, subtractions, multiplications, divisions, and exponentiations on x. And when I say exponentiations, that includes, let's say, an exponent of 1/2. So a square root would be an algebraic function. All polynomials, quotients of polynomials, polynomials and monomials raised to a power, square roots, cube roots of polynomials, and so forth. These are all algebraic functions. Here's a polynomial. It's an algebraic function. Here's the quotient of polynomials. It's an algebraic function. Here's the square root of the quotient of polynomials. It's an algebraic function. Now, let's contrast this with what we call transcendental functions. How's this for a definition? Simply put, a transcendental function is any function that is not algebraic. In other words, a transcendental function is a function that cannot be constructed through a finite sequence of additions, subtractions, multiplications, divisions, and exponentiations. The well-known transcendental functions include these: e to the x, natural log of x, all of the trig functions, and all of the inverse trig functions. It's probably going to be a while before you become exposed to any other transcendental functions. Probably in Cal 2 and Cal 3, these are the only transcendental functions that you're going to see. E to the x, natural log of x, all of the trig functions, and all of the inverse trig functions. So why am I telling you this? It turns out that we're going to have a need to express the composition of transcendental functions with their inverses in algebraic form. Now that sounds like a contradiction, but it's not, and I'll explain why in a second. This is going to seem like a contradiction. Trig functions and inverse trig functions are transcendental. We agree. But the composition of trig functions with inverse trig functions, and vice versa, can be written algebraically. So we compose one transcendental function with another transcendental function, and we get something that's algebraic. It's not as far-fetched as it seems. Consider this. These are inverses, so we should just get x. Composition of transcendental functions gives us something that's algebraic. This is a monomial. This is 1x to the first power. It's algebraic. It's a monomial. That being the case, it makes sense for us to be able to solve problems of the sort z equals trig function evaluated in inverse trig function of some expression in x. For example, z equals sine evaluated at arctangent of x over 2. Now, this is not a mindless or trivial pursuit. We actually have very good reason for developing skills in taking equations of this form and rewriting them algebraically. So we're not just doing this to be doing this. We have sound motivation and reason for developing our skills at taking an equation like this, written in terms of transcendental functions, and rewriting it in terms of algebraic functions. And we can do this when we have, for example, a trig function evaluated at an inverse trig function. So we're going to do some of these, and keep in mind, throughout this course, we're going to have a genuine need to be able to rewrite something like this algebraically. On your mark, get set, go. Now we're about to do something. We're about to do something really significant and praiseworthy. Write the given equation in algebraic form. Well, I'll tell you what, there's a lot here to get a handle on. And so just to make things easier for me to manipulate algebraically, here's what I'm going to do. I'm going to give the inner function a name. Here's the inner function, arctangent of x over 2. I'm going to say, let w equal arctangent of x over 2. Now remember what this means? W is the angle whose tangent is x over 2. And we're not really going to have to worry about the range here because we're going to work with right triangles. And if we're working with right triangles, we don't have to worry about pi over 6, 13 pi over 6, 25 pi over 6, and so forth. So W is the angle whose tangent is x over 2. Looks good. Draw a right triangle that depicts this relationship. W is the angle whose tangent is x over 2. Okay, so draw a right triangle. W is the angle. Tell you what, we'll put W right here. W is the angle whose tangent, what is tangent? Opposite over adjacent. The tangent is x over 2. So we can call the opposite and adjacent anything we want as long as they're in a ratio of x over 2. Opposite over adjacent is x over 2. So let's call opposite x and adjacent 2. What is there of any significance that we don't know about this right triangle? We don't know what the hypotenuse is. The hypotenuse is the square root of the opposite squared plus the adjacent squared, which equals square root of x squared plus 4. Okay? That's our hypotenuse. So let's put it up here. Here's our hypotenuse, x squared plus 4. Now we'll go to the third step. And maybe I'll put it down here. Rewrite the original equation in terms of W. The original equation was z equals sine evaluated at arctangent of x over 2. This is our original equation. And we're supposed to write it in terms of w. W is arctangent of x over 2. Son of a gun. There's our w right there. So this becomes z equals sine of w. Oh my goodness. We are so close. We are so close. Now we'll just rewrite the original equation. Using the right triangle. Z equals sine of w. Here's our right triangle. What is the sine? Isn't the sine opposite over hypotenuse? And the opposite is x, and the hypotenuse, square root of x squared plus 4. Z equals x over square root of x squared plus 4. We started out with transcendental functions. We rewrote it in terms of algebraic functions. We're done. And you know, it wasn't that hard. As a matter of fact, it's so easy, even I can do it. And you know what? If we get a few more of these under our belts, you'll be able to do it too. So let's do another one. Okay, here we go. This one's going to be just as straightforward as the last one. Now, how do we start this off? Do you remember? Look at what we got here. It's a mess. We can't grab a hold of the entire thing and work with it. It's just too much to work with. So what do? Right. We give the inner function a name. And we'll call it w. W equals cosine inverse of 3x. And what does this really mean in words? What does this mean? W is the angle. And we don't care between 0 and pi or negative pi over 2 and pi over 2 because we're working with a right triangle, so there's no need to make a deliberate restriction of the range of values here. If we're working with right triangles, we don't have to worry about, let's see, cosine inverse, that's 0 to pi. We don't have to worry about that. W is the angle whose cosine, W is the angle whose cosine is 3x. Okay, we're off to a good start. What's our next step? If you want to look at your notes, that's fine. Our next step, draw a right triangle that depicts this relationship. Okay, here's our right triangle. And W is one of the angles, so let's put the W right here. Might as well. And it says its cosine is 3x. Cosine is 3x. Now in right triangle trig, what is the cosine? Isn't it adjacent over hypotenuse? So we can call the adjacent anything that we want, and we can call the hypotenuse anything that we want, as long as they're in a ratio of 3x to 1. The simplest thing to do is say 3x to 1. Now, could we also say 6x to 2? Or maybe 3x squared to x? Yep, we could do all of these things, but why make it any more complicated than we have to? We'll call the adjacent 3x, we'll call the hypotenuse 1. So here's the adjacent, here's the hypotenuse. What don't we have? We don't have the opposite. And let's see. We know that opposite squared plus adjacent squared equals hypotenuse squared. And so that means that opposite squared equals hypotenuse squared minus adjacent squared, or that the opposite is equal to the square root of the hypotenuse squared minus the adjacent squared. And that is square root of 1 squared minus quantity 3x squared. And that's square root of 1 minus 9x squared. Okay. We got our opposite. And I'll let you look at that for a second before I add this to the triangle. Hypotenuse minus adjacent squared. Yeah, that looks good. So here's the opposite. It's 1 minus 9x squared. And on we go to step 3. What was step 3? If you don't know, take a quick look at your notes. Step 3, rewrite the original equation in terms of W. And it just so happens we still have the original equation up here. And W, we let W be the inner function. W was cosine inverse of 3x. That was our W. So the original equation is z equals cosecant of W. Now we're looking good. We are looking good. Step 4, rewrite this equation using the triangle. We're doing good. Z is cosecant of W. And let's see. I'm a bit rusty on my trig. Cosecant is equal to 1 over sine. And sine is equal to opposite over hypotenuse, so 1 over sine is hypotenuse over opposite. Cosecant of W is hypotenuse over the opposite. And so that's going to be 1 over square root of 1 minus 9x squared and there we have it. We've rewritten this algebraically in terms of z and x. We do a few more of these for homework and we'll be cranking these out like nothing.